Okay, so on to handout number 2 for chapter 8. So remember, chapter 8 is all about reactions with alkenes. What can we do with alkenes? So this handout has more unique alkene mechanisms. So before, right, they had a very reliable mechanism. The alkene was a nucleophile, alkene was a nucleophile. So here they're a little bit different, but it's still just acid-base electrophile nucleophile, promise, okay? So this first reaction is hydrogenation. We've actually seen this before when we talked about the stability of alkenes. I showed you guys, we talked about how we had unsaturated and saturated fats. And all that happens is that we have a formal reduction take place. We'll learn about reduction later, but just H2 adds across the double bond to give an alkane. Okay, so we just have an alkene like this. Remember, each alkene was a degree of unsaturation, right? Because it's not fully saturated with H2. So we just throw in some H2, and then we do need a metal catalyst to get this one to go. Palladium on carbon is my favorite. It's nice and easy to weigh out, just a nice black powder. You can also just use palladium, platinum, or nickel. You don't need all these, just an ore, okay? And in the end, you get out your alkane. So the alkene literally just gets reduced. Just all that happens is that we added H2 across the alkene. So it kind of just gets erased, is always how I see it. So yes, this requires just H2 gas. These reactions are really fun to do because to get the H2 gas into your reaction, we just fill up a balloon with H2 gas, put a little needle on the end of the balloon, and then put it in our reaction. Put it on top of the septum, through the septum of our flask. So that way it fills the atmosphere in our reaction flask with H2 gas, and we get fun balloons on our reactions. So again, this is the most common catalyst that this is done with. It's my favorite because, like I said, it's really easy to just weigh out. It's really nice, easy black powder. But we do need some sort of metal catalyst to get this to go. And we'll see, because we need the surface of the metal. We'll see that in just a second. Okay, so here are some examples. Here we have a benzene ring. This is actually styrene is the name of this compound. It's got an alkene over here on the end. Again, we just fill up our balloon with H2 gas. Weigh out some nice black palladium on carbon. And that alkene just goes away. Okay, importantly, the double bonds of the aromatic ring, of the benzene ring, are not affected, okay? They don't get touched. They are not affected. Okay, it's because they're super stable. They're actually very unreactive, okay? So just this lone alkene is what gets reduced, gets erased. Okay, we could also have this alkene. Again, we need some H2. And let's use some platinum here. And there it goes away, okay? So remember, again, these were just unsaturations in the molecule. Hopefully in lab you remember you can actually calculate the degrees of unsaturation for a molecule. Remember, each saturation is just an alkene, or we can have a ring, that too. So the mechanism of this reaction is complicated and weird, okay, because it requires surface chemistry, and so we don't really draw a formal mechanism with arrows and stuff like that. Instead, we draw something like that below. Hold on, I'll get to there. First, we got to introduce the overall reaction that we're going to show. Okay, let's start with this alkene. And instead of H, we're going to have some deuterium, so we can see the stereochemistry that results. And again, we're going to throw in some H2 and use our platinum catalyst. And interestingly, we're going to see that the H2 is going to add to the same face. Each H atom adds to the same face of the alkene. Same face of alkene. So, what type of addition was this? Do you guys remember the term? It is syn addition. Okay? So, as it's drawn here, kind of in these nice figures, so the platinum catalyst, the H2 just adsorbs onto it, kind of coordinates to the platinum catalyst, just gets stuck on there, okay? And the alkene with its electron clouds is also coordinated to the metal, it's attracted to the metal, and so it can also get adsorbed onto the, that's the word adsorbed, not absorbed, but adsorbed onto the metal catalyst, okay? And then once it does that, the H2 literally just kind of gets delivered, just kind of, here's my alkene, it just gets stuck onto the bottom face of the alkene, okay? Just gets stuck, and really the alkene coming from this side, but again, the H2 just comes right up to it. It's hard to see with my hands, but just goes underneath it. Okay, Okay, so it just really kind of gets delivered to the bottom face of the alkene. Importantly, it's always to the same face of the alkene, and then the product pops off. Okay, so you can imagine this guy can come in like this or like this, but in either case, the H2 just gets stuck to it. It's really kind of all that happens, okay? So because the two hydrogen atoms add from the solid surface to one side of the alkene, again, we say that they add with syn stereochemistry, okay? So let's say we have this alkene. Instead of deuterium, let's put on methyls. Throw in some H2 into our balloon. So use my favorite, palladium on carbon, just weigh it out. And all that happens is we get H2 adding to the same face. Okay, can the H2 add to the top? Yes, right, as in that methyl group going down and the H going up. But do you see that this is just a meso compound? It's an achiral compound. Same with the compound up here, it's meso. Okay, so that's why I didn't write the other enantiomer. But we can, here, I'll show that right now. How about this alkene? Okay, H2 in our balloon, and again, some palladium on carbon, Dr. Arpin's favorite. And what we're going to get, again, just imagine that H2 getting delivered. Let's deliver it from the top. Then those methyl groups go back, okay, because the H2 just added to the top. So those methyl groups go back, just like this. So what's hard about this is we rarely draw the H's. If it helps you, go ahead and draw the H's, and there's similar stereochemistry. Okay, but we can also get it adding to the back of this, right? And so that would push the methyl groups forward. Okay, so these guys are indeed enantiomers, and it will produce a racemic mixture. Again, that's because not again, but it's again because the alkene is flat, right? So we can deliver it from the top or from the bottom. Okay. Interestingly, let's say you can see here this is a trans alkene. Okay, this is a trans alkene. What if we used a cis alkene? Okay, let's see what happens. Let's use deuterium to kind of label actually where our reaction takes place. And so when we do this, okay, it still is going to get delivered to the same face of the alkene. So here we get deuterium just adding right across the alkene. Okay, we also get the enantiomer where the deuterium adds to the backside. Okay, but importantly, if we then rotate about this single bond, okay, the stereochemistry then looks anti. Okay, so when it looks anti, but we know that it's a syn addition from the mechanism, all that happened then is that we started with a cis alkene. So this is in your homework. You have to figure out how things can add anti when they normally add syn across an alkene. Okay, all that happened is that we started with a cis alkene. Okay, because when we do that, then when we rotate about that single bond, it looks like it added anti. But it didn't, okay? It still had the same mechanism. We can't change the mechanism, okay? So again, we do get the enantiomer here, and of course that is going to be racemic, okay? All right, so next up is oxymercuration-demercuration. This is just another way to hydrate an alkene. Hydration, right, was just adding water across an alkene. Okay, this is just another way to do that. And this is very useful because synthetic organic chemistry, you definitely need more than one way to do stuff. Okay, there's lots of reasons why we should have more than one method for the same transformation, okay? And that's because, first off, lots of alkenes don't undergo hydration in aqueous acid very readily. Okay, that's because they can be insoluble and they can undergo side reactions and all those things we don't want. Okay, so that's just normal hydration with catalytic acid and water. Okay, so oxymercuration-demercuration is nice because it converts, again, alkenes to alcohols, or we'll see we can also do this with ethers in Markovnikov fashion. And this mechanism is different, okay, and we do not have a full carbocation, which removes the possibility for rearrangements. Okay, and that's very, very useful here, okay, because again, if we did it normally as a normal hydration, we might get a rearrangement, but if we use this method, right, to do the same reaction, we would not get a rearrangement. So it's always good to have more than one method to do a certain synthesis, okay? So just like the hydroboration reaction, that's one we just learned today, Wednesday, the BH3 reaction, okay? This is a one-pot, two-reaction process, okay? And it utilizes mercury acetate in the first step to form a mercurinium ion, and NaBH4 in the second step to reduce the mercury. All right, here we go. This is what it looks like. So again, we have our alkene, and as it says, we need our mercuric acetate, HGOAC2. I'll show you what that looks like in a second. We do need some water here, right, because water is a nucleophile. And then we throw in step 2, right, this is a one pot but a two-step reaction, NaBH4. Okay, right, and the whole one pot part is we'll just let it stir with these first reagents for a little bit, for like an hour, and then we'll throw in the second set of reagents. So it's still the same pot. We don't like isolate any intermediates or isolate anything in between. It's one pot, we just kind of wait in between adding the reagents. And in the end, we get Markovnikov hydration just via a different mechanism. Okay? So again, this is Markovnikov addition of H2O. Okay? But we're going to see it goes through a different mechanism than what we saw before. Alright, so again, this is a unique mechanism. It's a little bit longer than what we've seen, but don't worry, have no fear. Okay, so we have our alkene again, and we need our mercury acetate, and that looks like this. HGO, this is an acyl group, kind of like acetone, right? OAC, so that's HGOAC2. Mercury can have an expanded octet, but well, this just has these two electrons on it. So, just like the Br2 or X2 reaction, okay? The alkene is still a nucleophile. It actually attacks the mercury and kicks off one of the OACs, okay? And just like the bromine or the halogens and forming the halonium ions, right? We can come back and prevent the carbocation formation, okay? Just like with X2. Okay, so let me write that really quick. Again, just like before, the alkene is the nucleophile. Okay? We break these electrons. Sorry, we break this bond again. Break like SN2. Okay? And then the mercury's electrons come back. And again, that is just like reaction with X2. X2. Sorry about that. It's a weird X. Okay? It's the same thing as with X2. Okay, we attack the mercury, we kick off one of those acetates, and meanwhile mercury has electrons, it can come back and prevent carbocation formation, so it does. Okay, and so the intermediate looks a lot like the halonium ion, just with mercury. Hg. It's got one of those OAC groups still on there, and it's got a formal plus charge. Okay, so this is our mercurinium ion. And again, just like with X, when X is here, the carbons are electrophilic. So we have water in there, right? And so the water can come in and attack. And importantly, just like before, when we have a choice here of which carbon it can attack, because again, it's just like with the halonium ions. We are electrophilic at the carbons. Which carbon is more electrophilic? The tri-substituted one, well, tetra if you count the mercury, or this one, the less substituted. Which one's more electrophilic? Remember, it's the most substituted. Okay, so this guy is going to go in and attack the most substituted carbon, and then we're going to break towards the mercury, just like what we did with X2. Okay, so we get here, water has added, and we still have our mercury, HGOAC. Okay, so importantly, right, the nucleophile, ooh, I need to write a lot here. nucleophile still needs to attack the backside. Attacks backside, importantly, of the most substituted carbon. Okay? And that is again because it's the most electrophilic. Because we'll say it has the largest partial positive, right? And that's what makes it the most electrophilic. Okay? And right, that's again because the electron density is being pulled towards the mercury, so it renders the carbons actually electrophilic, and we can bear the most partial positive charge on that most substituted carbon, so it does so. Alright, so now we're here. Right, we can't isolate something like this. The last step is just deprotonation. Not the last step. We're almost there. Go ahead and deprotonate. So you can see that our alcohol is in place. All we have to do is get rid of that mercury. HgOAC. Okay? And so all you need to do is throw in NaBH4. NaBH4. Okay, so again, all that's going to happen here, kind of like with the BH2 just turning into the OH, here the NaBH4 just turns the mercury into an H. That's all that happens. Okay, so here this just turns the mercury, becomes H. Okay, it's a reduction mechanism, so we'll learn that later, but importantly right now we don't need to know it. Okay, it's really long, so we don't need to know it right now. Don't need to know mech, but it is a reduction, which we will see later. Okay, so again, okay, we add to the mercury, kick off the acetate, just like with X2, those electrons on mercury come back. We form the mercurinium ion, which is most electrophilic at the most substituted carbon, so water comes and attacks, we deprotonate, and then all that we have to do is get rid of that mercury, and we do that with NaBH4. Okay, so importantly though, this can also be done, we don't have to limit ourselves to water, and this is true with our hydration mechanism too. We don't have to limit ourselves to water. This can also be done with an alcohol. Instead of just HOH, we can use ROH as our nucleophile. Okay? So look out for that in your homework. Okay? So again, that's just ROH adding, and so then, ROH adds just the oxygen, still we'll just add, and then again, all we do is just deprotonate that H, so that would just be OR. So then again, it looks like an ether. So then in the end, it looks like an ether as opposed to an alcohol. Okay, and this can be done also with normal hydration mechanisms. You don't have to just use water. We can use alcohols. Okay. And just like with halohydrin formation, the regiochemistry of this reaction is such that the nucleophile attacks the most substituted carbon. Again, it attacks the backside, right? The regiochemistry is that it attacks the most substituted carbon, and for the stereochemistry, right, is it attacks the backside. So the OH and the H actually end up with anti-stereochemistry because it's got to attack the backside. Okay? And that is because that is where the antibonding orbital lies. Okay, so it has to attack the backside to attack the sigma star antibonding orbital of the C mercury bond and break it. Okay, it's got to attack that backside. So let's go through this mechanism one more time with this alkene. Again, our one pot, two-step reaction. We first need our mercury acetate. Okay, let's do this with ethanol. Show how this can be done with an alcohol. And then II is just NaBH4. Okay, just is going to turn our mercury into H. And the products we're going to get, we will see, is where we have that OET and the H add anti. Okay, we don't normally draw H's, but I'm doing it for effect here. We can also get the enantiomer, of course, because the alkene is flat. And so we can get the OAT on top. And again, importantly, the H is going to be anti. Okay, this will be racemic. And importantly, we get anti-addition. Okay, so the mechanism, right? The alkene is a what? The alkene is a what? Nucleophile. So let's draw our mercury here. You can just abbreviate OAC. We attack the mercury and kick off. Meanwhile, mercury's got electrons that can come back. Okay? And we form our what ion? The mercurinium ion, and importantly, right, that can form above or below, on top or on bottom of that alkene. Okay, so we have our mercurinium ion. Yes, we can form the other enantiomer. Okay, but when we have our nucleophile in there, which again is not water, but is instead ethanol, because that's what we have in there, right? If this mercurinium ion is going down and we have to attack the backside, from what side are we going to attack? Top or bottom? Right, we have to attack the backside. We're going to attack from the top. So let's see if I can draw that to try and add some stereochemistry. Add from the top. Whoa, that's a big arrow. Okay. It must attack top. Okay. So in doing so, that methyl group gets kicked down. So here's the methyl group. Here is my alcohol, OHET, formal plus charge, and that mercury still ends up down, HgOAC. Okay, so one more main step is just deprotonation. We'll just go and deprotonate. Okay. So now we have an ether on top, OET, that methyl group, and still my mercury, HgOAC. So importantly, the methyl group got kicked down. Gets kicked down. Right, because it was on top over here. Okay, so it gets kicked down now because of the attack from the top. Attack from the top, so the methyl group gets kicked down. Okay, and all that's left, right, is the NABH4. And all that's going to do, it's going to do it with the same stereochemistry. It just turns that Hg into an H. Okay, and we do get the enantiomer, of course. Okay, so we can see here again that the nucleophile and the H have ended up anti. Okay, and that's because it has to do it with anti-stereochemistry. Oh, -5, Dr. Urban. Sorry. Forgot my breaking arrow right here. Don't you forget that arrow. Okay, it's got to attack the backside to break that bond. Okay, and this methyl group still kind of keeps disappearing from us. Sorry, it's there, that methyl group. Okay, and that gets kicked down here. Alright, so that's oxymercuration-demercuration. That's a lot of syllables.